Okay, so we are starting with an introduction to our uh, organization, CASI Lab. Um, so, good evening, everyone. It is a privilege to introduce you to our center, the Center of Advanced Studies and Innovation Lab, CASI Lab in short, located in Silchar, Assam. Since beginning its journey in 2018, CASI Lab has been working to develop a conducive research ecosystem in the sciences, primarily focusing on mentoring project-based studies for undergraduate, postgraduate, and research students, as well as organizing a series of in-person and online talks. We are firmly committed to providing a democratic, borderless ecosystem that bridges the gap between institutional experts, independent scholars, and grassroots researchers by facilitating collaborative projects regardless of geographical constraints. As we proceed with today's seminar, I invite you to view our modest efforts through the lens of CASI Lab for the greater good. It is a privilege to have with us this evening Professor N.D. Haridass, a leading theoretical physicist whose work has significantly shaped areas such as quantum field theory and the foundations of quantum mechanics. Today, he is going to deliver the inaugural lecture of our series on the topic on varieties of quantum measurements. Sir, we are honored to have you with us. The floor is yours. You can start.
Thank you very much. Thank you for inviting me to talk in this series. I must congratulate Kasilab on taking on all these very, very important activities. And I wish all of you the very best. And I wish you success in reaching the highest levels of academic excellence through your efforts. Thank you. So today I'm going to talk about varieties of quantum measurements. But before I do that, I would like to pay tribute to what I call two science heroes from Northeast. And the first of them is Professor Kamalendu Deb Crowry. He is 96 years now and going strong. He was the principal of the Cotton College, Guwahati. He has authored books on general relativity, thermodynamics, and quantum mechanics. And he is a pioneer in general relativity research. His Crowry-Barua singularity-free solution is famous and highly cited, and many other important works he has carried out from Assam, Northeast. So we should all be very proud of his achievements, and he should be role model for youngsters, not only from Northeast, but from all over India. Apart from this famous Crowry-Barua solution, he has worked extensively on many other topics like exact solutions and even on implications for neutrinos. He was recently honored with the prestigious Vaidya Rai Chaudhary Endowment Lecture of the Indian Association for General Relativity and Gravitation in 2000. So it gives me great pleasure to pay my tribute to this hero of Northeast, hero of Indian general relativity research. The next hero I would like to pay tribute to is Professor Dilip Kumar Chaudhary. As you can see from that picture, we were classmates in our MSc days from Delhi University, and Dilip is on the top standing row, second from left. We have been very, very close friends ever since 1965. He was a leading expert in quantum chromodynamics. In fact, he did very important work at a time when there was a lot of confusion and darkness in this area. His work was so important that it was mentioned by Burton Richter in his Nobel lecture in 1976. He worked with leading physicists like Richard Dalitz after getting his PhD with Professor A.N. Mitra. Professor A.N. Mitra was also the person with whom I did my master's thesis work on quark model. And Dilip authored recently a book called 50 Years of Quarks and Gluons. And this is published by the PANE, of which he was the founding vice president. And in this booklet, he recounts the many exciting topics he worked on. In addition to all this, he also contributed to spreading the physics culture in Northeast with several writings in Assamese. And it's very important that as many of us as possible write in our local languages, as that is a very, very important channel to propagate science. So now I will go on to the topic of today, quantum measurements. Now, when one hears the word quantum measurements, one maybe typically thinks of the famous Stern-Gerlach experiment or some NMR experiment, etc. That's of course right, but actually quantum measurements span a lot more. Here I show you a picture from the Light Hadron Collider, which is an accelerator experiment. This too is a quantum measurement. In a lighter vein, one could say that when you eat the famous Shosher Hilsha, actually many quantum measurements are going on, okay? So today what I want to do is give you a very broad overview on quantum measurements and why and how the rules for quantum measurements came about. Now, first of all, whether it is classical physics or quantum physics, measurements bridge theories with their physical interpretation. So there can be no science without measurements. And in that sense, physics is deeply an experimental science, but the beauty of physics is very high caliber experiments go hand in hand with high caliber theories. And the result of this is we have seen an enormous growth in our understanding of the physical universe, particularly in the last century. Now, in classical physics, no explicit rules for measurements need to be given. Like, for example, if you measure a current through an ammeter, you don't have to state any more than whatever is already needed to understand currents, charges, etc. But in quantum mechanics, it turns out that you need additional rules to say what are quantum measurements. And such rules are essential to actually make sense of the theory. Now, the two great breakthroughs in quantum mechanics were matrix mechanics due to Heisenberg and wave mechanics due to Schrödinger. And even after both matrix mechanics and wave mechanics had very successfully accounted for the spectrum of hydrogen-like atoms, the physical interpretation of quantum mechanics, and in particular, what is the observable content of quantum theory, remained highly obscure. And some very important milestones had to be crossed in order to get a clearer picture of these subtleties. I list some of the main milestones in somewhat chronological order. First was Dirac's statement of the principle of superposition of states. And the great importance of this principle of superposition is the principle of superposition of states, not of sound wave amplitudes or of vectors or of other kind of superposition, which we already heard. And if you want to truly appreciate the depth of superposition of states, I encourage you to read the early volumes of Dirac's classic book on quantum mechanics. And the upshot of that is that, in fact, the principle of superposition of states can be taken to be the definition of quantum theory. If somebody asks you, give me a one-line definition of quantum theory, you say it is those theories in which there is a principle of superposition of physical states. The states part of it is very important. And the next milestone was the probability interpretation due to Born and uncertainty principle of Heisenberg and the complementarity principle. Though this sounded somewhat philosophical, today we can understand this in modern terms without necessarily having to go through the philosophical, I don't know what to say. In fact, it is in conjunction with the complementarity principle that Bohr made the visionary recognition that measurements play a very central role in our consistent interpretation and understanding of quantum mechanics. Now, I would like to take you through some little bit of historical detour. Einstein's role in the development of quantum mechanics has been commented on, and there are enough sources that it would take us a lifetime to even get through a part of that. Today, I want to tell you a little bit about Einstein's role in the development of the uncertainty principle itself, because this may not be all that well known. So in a meeting with Einstein, Heisenberg is supposed to have told Einstein about how he had followed Einstein in not allowing unobservable elements in the formulation of quantum theory, because at one point, Einstein held that unobservable elements should not enter a description of theory, and this attitude he held mostly during the development of special theory of relativity, when things like absolute simultaneity, etc., he argued, they are unobservable, and therefore the theory should not be formulated involving them. Now, in the case of Heisenberg's discussion with Einstein, the unobservable elements were the particle orbits or trajectories. As you all recall, Bohr's atom heavily depended on maintaining the picture of electron orbits. And even with Sommerfeld's remarkable generalization of Bohr's model, the orbits were very much there. And as all know, that this led to a series of very difficult conceptual questions. And Heisenberg's bold step was to formulate the behavior of atoms without invoking the orbits. So he, in fact, claimed that he had sort of outlawed the orbits from the description of atoms. To this, Einstein is supposed to have responded, firstly, that he no longer believed in that way of thinking, namely that what is not observable should not enter the description of a theory. And in fact, Einstein said something very deep, that it is the theory that determines what is observable. Therefore, you'll get into logical difficulties if you say not going to allow unobservable elements in a theory without knowing what the theory is and without knowing what the theory determines to be the observable content. Okay. So here is a picture of tracks in a cloud chamber, and I'm sure all of you have seen it. It's quite thrilling to see these tracks, and at first sight they look like their orbits are there, quite sharp, quite visible, quite real. So Einstein questions Heisenberg's vanquish of trajectories by saying, but you refuse to consider orbits even though we can observe tracks in a cloud chamber. How can this be possible? At first, Heisenberg was unable to give a satisfactory reply to this very sharp critique of his whole program, and a lot of thinking about it led to his formulation of the uncertainty principle. It's not that orbits per se have to be banished from quantum mechanics. It is that orbits can only be included with certain degree of imprecision. And the degree of imprecision was mathematically precisely formulated by Heisenberg, not in the paper, but later on. Now, another pillar of quantum theory is the probability interpretation. And Einstein played a big role in this also. In his beautiful 1917 paper, by the way, I encourage every youngster to read these originals. They're very, very readable, unlike most of the modern day papers, where after reading 2 lines, you have to go chase a reference. And after reading 1 line of that, you have to chase another reference and so on. These papers are self-contained and they give important, they mirror the thinking that went into these developments. So in this paper, he emphatically stated that chance will be an inevitable aspect of quantum theories. There is another aspect of Einstein's contribution to the probability interpretation, and I have not yet traced the source, but in Heisenberg's 1927 paper, he says Einstein, already in 1925, formulated a statistical interpretation of de Broglie waves, and he goes on to say that this work of Einstein played an essential role in subsequent developments, notably the Born interpretation. So I want to make a small commentary about Born and the probability interpretation, because it's a knee-jerk reaction now that we attribute probability interpretation to Born, and in particular to the paper he wrote in 1926, where he proposed the probability interpretation. But that paper, Born's original paper, apart from being motivated by many incorrect considerations, it had fatal flaws. Throughout the main body of the paper, he maintained mod psi to be the probability measure. And in this, he was influenced by many others who also thought it was plausible that mod psi is the probability measure. Only in a footnote to the paper, Born changed the stand, but now proposed that probability was proportional to psi squared, which we all know now is completely wrong. So the paper is full of errors, and this has been pointed out by others like Abraham. Now in 1926, von Neumann undertook a very systematic study of quantum theory. Most of us, even me included, for a long time, used his very famous book on mathematical foundations of quantum theory as the source, but he actually wrote 3 papers in around 1926-27. And the second of those papers is where he really laid, many of the foundations of quantum mechanics, including notion of quantum states, quantum observables, and quantum measurements. Now, von Neumann criticized Born's approach for not being systematic, because von Neumann himself was extremely systematic. In fact, he called Born's ideas to be dogmatic identification of absolute scales with probabilities. Dogmatic because Born gave no compelling reasons why such an identification ought to be made. It's also worth emphasizing that the entire Born interpretation actually needed a theory of quantum measurements, because it says probability of finding something. Now, what is this finding if not a measurement? Therefore, even though Born had given the probability approach, a complete understanding of that had to wait a proper understanding of quantum measurement theory itself. Now I come to another pillar, just refer to what I said about Dirac's comments on this, and this is a superposition principle, quantum superposition principle, and its intimate connection to quantum measurement. So let's take eigenstates of some observable, which is Hermitian, taken to be Hermitian, and their corresponding eigenvalues. Now, principle of superposition of states says that if you make a superposition of eigenstates with some complex weight factors, subject to some restrictions like total norm B1, then this is a bona fide quantum state. And therefore, one can ask, what will be the outcome of measurements on this physical state? And this is, in fact, a very difficult question that was faced in the beginning, namely, what will be the outcome of a measurement of A on the system in this state? It is important to emphasize that an answer to this question depends as much on the state psi as it does on the characteristics of the measurement process itself. So let us be specific and take these measurements to be of the type propagated in the standard law, measurements whose outcomes are eigenvalues randomly, the so-called projective measurements of von Neumann. In fact, these were the first type of measurements that he proposed in that second paper that I already mentioned. And why he arrived at this particular type of measurements is something really worth understanding, and I refer you to that second paper. Also, von Neumann stated that after the measurement, the state of the system becomes the corresponding eigenstate, and this is called the state reduction, of the post-measurement state, and also loosely called the collapse of the wave function, a name which unfortunate and has caused a lot of confusion, and so we will avoid that and instead say state reduction post the measurement. Now, clearly, eigenvalues and eigenfunctions play a very important role in this construction, and it is important to understand the precise genesis of the eigenvalue, eigenfunction idea for the physics of quantum mechanics, because both of them are purely mathematical notions which existed in the study of matrices long before quantum mechanics was born. So why is it that these purely mathematical notions play such a central role in the physics of quantum mechanics? So in the matrix model, Heisenberg identified the eigenvalue of the Hamiltonian to be the physical value of energy in a stationary state. And the empirical vindication of this was the agreement with the term values for the spectra of hydrogen-like atoms. And the corresponding eigenstate was identified as a quantum state of the hydrogen atom with well-defined energy. Now, at the time of Heisenberg's paper, for other observables, how many other observables are there, etc., etc., there was no logical necessity to require this. It was Dirac who suggested that this hold for other observables too, based on his transformation theory. And it was a very innocuous looking suggestion, but had great impact on the development of quantum mechanics. In fact, the consequence of the seemingly innocuous idea of Dirac are very deep, and in fact gave rise to the principle of superposition of states. If you want to go deep into this matter, I refer you to a talk I gave on the 100th anniversary of the Bohr atom, where I tried to trace the origin of the principle of superposition, because it's the principle as deep as the principle of equivalence of general relativity, or principle of relativity and special relativity. And yet, exactly how this deep principle, what is its genesis, is not that well elaborated in either textbooks or source. Now, I'll continue to make a few more remarks on superposition and measurements. The Born probability rule was originally formulated in the context of describing collisions in quantum theory, and this should be generalized now in the context of the superposition to say that the outcome AI occurs with probability AI psi squared. This brings to the fore two other fundamental aspects of quantum measurement. If you have a single copy of a wave function, then sequential measurements have no significance, because after the first measurement, it becomes one of the eigenstates, and subsequent measurements will only give eigenvalues with no information about the original state. And in fact, the way to escape this is to say that only measurements on an ensemble of states is meaningful in quantum mechanics, and the statistics of measurements on ensembles is what gives information and about the state and determines the post-measurement state on an ensemble is no longer represented by a wave function, but by a density matrix, in particular a mixed density matrix. And all these aspects, as you all know, are essential to understand a wide variety of quantum mechanics. So at this point, you can raise several foundational issues. Are measurements of this type, namely eigenvalues as outcomes, even consistent with the theory? In other words, can you give a formulation of these kind of measurements based entirely on the formalism of quantum mechanics? And a more important question, and the answer to the first question is, of course, yes. And that was the von Neumann model of quantum measurements, even though there are still some outstanding difficulties with that model. The second question is, are they the only type of measurements allowed by the theory? Now we go back to what Einstein said, that it's the theory which determines what's observable. We can interpret that remark as saying it's the theory that determines what type of measurements that can be made, and the type of measurements will tell us what are the observables of the theory. Of course, the recipe that outcomes are eigenvalues with corresponding state after measurement being the eigenfunction is at least self-consistent, in the sense that if you repeat the measurement, then it follows the same rule. And in fact, this is how von Neumann arrived at this class of measurements, by requiring what he called the repeatability criterion. That if you immediately repeat the same type of measurement and the outcome, then you must get the same result. Now we will soon see that now we have a plethora of measurements which do not respect the repeatability criterion of von Neumann, and yet are bona fide measurements and are perhaps in much greater use than the productive measurements themselves. So therefore, repeatability is not a necessary requirement for meaningful quantum measurement. And if that repeatability is not there, have we lost something? Because in physics, we want all results to be reproducible, repeatable. So have we lost it? No. It turns out that we have to interpret repeatability in a much broader sense than what von Neumann had initially done. For example, I can give one rule of measurement that is quite consistent. Suppose the rule is that the outcomes are expectation values of the observable you have measured, and the state remains the same. Now, since the state has remained the same, if you repeat the measurement, you'll again get the expectation value. Okay? So you can, in principle, have measurements which are not necessarily of the eigenvalue, eigenfunction type. Of course, there could be several objections to such a proposal. For example, it goes the crude dictum that quantum measurements, unlike the classical counterparts, always disturb the system. First of all, this is a very, very vague statement, and this is, we will soon see that this is an objection without any substance. More serious objection comes from linearity, because if the disentangled initial state of the system and apparatus is such that the system is unchanged, but the apparatus reading changes to the expectation value, on the left-hand side, the state psi occurs linearly, and on the right-hand side, the state psi occurs non-linearly. And this will not work. And in fact, this is somewhat similar to the argument that is invoked in the no-cloning theorems. It doesn't rule out such type of measurement. It only says, okay, I cannot realize such experiments on all states, but maybe there is some small subset of states on which such measurements can really work. If they work even on a small subset of states, it's still very significant. The punchline is really Albert Einstein's statement that it is the theory that determines what's observable. Now, I will elaborate on a few such possibilities. But before that, we come to an important issue, the apparatus. Bohr took the view that the apparatus, even for quantum measurements, must necessarily be classical. And he gave some very hard to understand philosophical considerations, including the nature of language used in our communication and description of physical phenomena. Nevertheless, that was a point. What he meant was that you cannot use another microscopic quantum system as an apparatus in a quantum measurement. Von Neumann, on the other hand, took the opposite stand. He said that, look, classical apparatus is also made up of atoms, and they obey quantum mechanics. So why should the apparatus be singled out? And he disliked what he called Bohr's two worlds interpretation. Namely, the system is quantum mechanical, the measuring apparatus is classical, and he proposed that the apparatus also be described by a suitable quantum system. But now we'll see that what we really mean by apparatus itself will become more and more complicated and nuanced. The resulting von Neumann measurement model has had many successes, but it has also had deep conceptual problems, of which the so-called collapse of the wave function is the most formidable one. There have been many recent quests into the question of, can we talk about the degree of quantumness, and in particular, the degree of quantumness of macroscopic objects? Macroscopic in the sense they are made up of a very large number of atoms, each of which obeys quantum mechanics. So these questions are extremely important, and they have come back, and we should look forward to future developments which are very exciting, and clearly quantum technologies are going to play a very important role in addressing some of these questions. So Dipankar Home is one of the pioneers of this quest of determining how quantum can be or not be macroscopic systems. Now, here is the von Neumann model. This is the original Stern-Gerlach model, where to the left you have a source of silver atoms and an inhomogeneous magnetic field, and some distance away a screen where silver atoms get deposited. Now, these three stages are very important. There are three stages that has to be kept in mind. First stage is the initial state preparation, both the system and the probe. And in the case of this Stern-Gerlach experiment, it turns out that the system is the spin degrees of freedom and the probe are the position degrees of freedom of the silver atom. So in a sense, they reside on the same quantum system. So there is a measurement interaction that produces the required one-to-one correspondence between the system and the probe. And this happens when they traverse the inhomogeneous magnetic field. But this is a completely unitary development and does not constitute the full measurement. So the question is, where is the measurement completed? And the answer in this case is that it's completed on the screen. Now the screen is a very complex system having macroscopic number of atoms, which is called environment. And therefore there's an interaction finally between environment and the system and the probe. This is the part that is least understood about quantum measurements, but often the second stage, namely of measurement interaction and completion of the measurement, are confused, but they should not be. They're very, very distinct, and we have no conceptual issues with the measurement interaction part, but we still have a lot of conceptual problems in addressing where the measurement is completed and how it is completed. For the initial state or the pre-measurement state is taken to be what is called a disentangled product of the system and the probe. And the phenomenon considers the interaction between these to be impulsive in the sense that it acts for a very, very short duration. And in the Sanger-Locke apparatus, this can be achieved by making silver atoms with sufficient velocity as they go through the inhomogeneous system. So they spend very little time. And when the impulsiveness is valid, then you can forget about the Hamiltonian for the evolution of the system and probe, and only the interaction Hamiltonian becomes important, and that is very simple. So you can apply it to the state of the system before measurement, just the unitary operator, and it gives the expansion. So you can expand the state psi in terms of the eigenstates, as we already talked about, and S in the measurement interaction just picks up the eigenvalue corresponding to that, and this is what you get. Now you can call the red state here a new state of the apparatus and call it phi I. Now there are technical issues that these should be nearly orthogonal, and for that, phi naught cannot be arbitrarily chosen. It has to be an eigenstate of a variable that is canonically conjugate to the probe variable that enters the measurement interaction. So after the measurement, you have the following state, but this state is an entangled state of all possible measurement outcomes. If the measurement outcome of the probe is phi I, then the system will be in SI, but this is an entanglement of all possibilities. So you can't say that this will have produced a single outcome, which is what should characterize a measurement. Now, how do you solve this? Initially, it thought that you need a second apparatus or probe to look into the first one, but that doesn't help. You again end up with another entangled state, and this is called the infinite regression, and was a very serious problem. And even Wigner at one point seriously suggested that consciousness has to play a role in that, but in many sense, consciousness entering the physics verbiage has to be done with extreme care, and so this was not very seriously taken, even though it came from Wigner. Surek pointed out that, look, in the end, you have this environment to think about. In the Sanger-Locke experiment, it's a screen, and you have to see what happens. There's a huge number of atoms or molecules of that screen, and they're all interacting, and there is no way to keep track of, individual evolution, and you have to somehow treat this problem. And the effect he claimed is to decorrelate the various elements in the superposition into, instead of a superposition of states, it becomes a mixture of probabilities. Incidentally, Bohm had considered such thinking long ago. And in his very deep book on quantum mechanics, he essentially said this without bringing in environment and decoherence, etc. Now, decoherence is due to this interaction between apparatus and environment, and it has to pick out a preferred basis for the apparatus, because this diagonalization cannot happen in every basis. And that is the sticky point about decoherence. Quantum mechanics is basis independent. So how can this decoherence mechanism pick out a specific basis without violating quantum mechanics in some form? Now, this is a deep issue, and I won't go further into it because I've already taken up a lot of time without having gone through even half my talk. And there are some other issues with decoherence, decoherence times, etc. But today, technology has improved to a stage where controllable decoherence is becoming technologically feasible. So the decoherence picture should be put to stringent experimental tests. In the end, it may turn out that decoherence is sneaking in the very answers that it has sought, and that it's not an answer to the question of collapse of the wave function, because in some subtle way, it has already used the collapse of the wave function in its treatment. So according to me, one of the principal challenges for condensed matter physics, this is a problem in condensed matter physics, is to provide a detailed elaboration of decoherence, but condensed matter theories too use all kinds of schema like reduced density matrix, etc., etc. But one has to carefully deconstruct those steps, because you should not have assumed the answer to the question that you are trying to answer. Now, where does decoherence take place? So here is the Stern-Gerlach apparatus on the left side, and I can repeat it. If I don't put the screen, I can again set up another inhomogeneous magnetic field, and I can just get back the original state. Therefore, decoherence could not have taken place at the stage of the interaction with the inhomogeneous magnetic field. So it's not at the magnets, because then multiple Stern-Gerlach experiments would be impossible. This multiple Stern-Gerlach experiment is what Schwinger called putting Humpty Dumpty together. Okay? Whereas in a situation where decoherence or the diagonalization has taken place, Humpty Dumpty cannot be put together. So here's a summary of the Farnaman measurements. It's impulsive. Only eigenvalues are outcomes. Expectation values of properties can be measured in a statistical sense. Measuring complete set of properties leads to a determination of the state, and this is called the tomography, and there is irretrievable damage to the pre-measurement state. Now I come to the next important development, the Heisenberg microscope. I will not describe it because everybody has by now read about it, thought about it in their own way. But basically, Heisenberg identified a fuzziness in the value of position dictated by resolving power, and a fuzziness in the momentum value because of the uncertainty in the direction of the photon. And he put together, note, he used small delta, delta phi, delta x, and he didn't write an equality. He wrote an inequality which serious-minded mathematicians would simply rubbish because it really is too vague and approximate. Whereas the uncertainty relation that as we now understand involves not small delta, but capital delta. And it is not some fuzzy inequality, but it's a definite inequality with a definite bound on the right-hand side. But this form is about variances. Delta P, delta Q are not fuzzinesses. They are variances in the statistics of the ensemble of measurements. Whereas in each ensemble, so imagine your ensemble to be split into two, and on one you make position measurements, and another you make momentum measurement. Both these can be made with arbitrary precision. Okay, so there is no fuzziness, and they can yield short values, but it's a distribution that is captured in this. In the Heisenberg microscope, it was one single fuzzy measurement, whereas in the modern version of uncertainty principle is a statement about ensemble measurements. So these two should not be mixed up with each other at all. There were various lacunae with Heisenberg's paper, and of course, only Niels Bohr understood what those were, and he severely criticized various aspects of this thought experiment, but agreed that some form of uncertainty principle is indeed a hallmark of quantum theory. The microscopic experiment talks about the limitations of measuring position and momentum simultaneously. It does not really say anything about the outcomes unless additional stipulations are made. In particular, Heisenberg tacitly assumed that it makes sense to assign values to observable before measurement, and that measurement yields these values, although limited by the fuzziness. This latter point is completely orthogonal to at least the Copenhagen way of looking at quantum mechanics, where you cannot assume or assign any value to observables before a measurement is made. So these, according to Bohr, were some very serious problems with Heisenberg's thinking. In particular, what he pointed out was that uncertainty in momentum need not be there, because you could make a very precise measurement of which direction the photon was emitted, and then you cannot say the recoil is an uncertainty. Okay? And in fact, Bohr analyzed in depth exactly how that should be carried out, namely how the subsequent measurements on both the particle and the photon have to be done. I'll cut short, this because I'm running a little bit behind time. And it's also clear now that with single photons, it's meaningless to talk of interference. And this has been vastly and beautifully demonstrated through ensemble measurements, where step by step, the so-called interference pattern gets built up. So is there a way of understanding simultaneous measurement of position and measurement, which the Heisenberg microscope tried to attempt? In other words, we want to look for a modern variant of the Heisenberg microscope. And there is indeed a very beautiful treatment of this problem. Here we simultaneously measure, in the von Neumann sense, both the position and the momentum of a particle. If P hat, Q hat are the position and momentum operators of the quantum system, non-commuting variables, the Arthur-Kelly proposal is, instead of one apparatus or one probe, Now you introduce two quantum mechanical systems, X capital Px, Y capital Py, satisfying the Heisenberg uncertainty relations for both X and Y, but otherwise X commutes with Y, Px commutes with Py, and they can be simultaneously measured. So the measurement interaction is taken to be very similar to what we took in the Feynman measurement, except that now we are talking about momentum and position and not spin. And this is the typical Hamiltonian, which is Hermitian and very good. Sorry. Now again, the pointer states of Feynman measurements, M and N have to be chosen to be, eigenstates of the canonical conjugate variables. And you can take this particular representation, and here we have chosen only one parameter, B. That is not really necessary, but for optimal measurements, it turns out that you should choose the same parameter. It's a technicality which we don't have to get too involved to appreciate the spirit of the Arthur-Kelly measurement. So initially you take the quantum system and the probes, Mn, disentangled state, and then a little bit of algebra is required to find out the post-measurement state expressed in the variables, position variable of the quantum system, and Xm by M are outcomes of the M register and N register, and you can show that it has this simple form. One thing to notice is that the width of the distribution in Q now has increased by square root of 2, and this is not because of this particular choice, but it is generic, and in fact arises from a very deep result that measuring incompatible observables simultaneously necessarily adds noise. Okay. So now you can take Xm to be the outcome of a position measurement and Ym to be the outcome of a momentum measurement, and you have a distribution experimentally determinable, which is really a phase-space distribution. But each measurement output is random and unpredictable, exactly as in the single variable measurement. And after each measurement, the system changes to a wave packet centered around the observed value of momentum and observed value of position. And the memory of the original state is completely lost, as in the original Feynman measurement. Here too, you have to perform ensemble of measurements, and the product of uncertainties turns out to be, this is the optimal one, delta P, delta X is not H bar or 2, but H bar. So this is that noise that I already talked about. Now the distribution is analog of the Wigner distribution in quantum mechanics. But the Wigner distribution is a quasi-probability distribution because it is not positive everywhere. In fact, the regions where the Wigner distribution turn negative are crucial for understanding quantum interference. In contrast, the measured XM-YM distribution is always positive because it is certain frequency that you observe in a measurement. But it's known in quantum mechanics that even a tiny amount of smearing can make Wigner distributions positive. Therefore, what the Arthur-Kelly measurement is to directly give us such smeared Wigner distributions which are positive. And one such is the so-called Husimi distribution function. And now, by various choices of the Arthur-Kelly type of measurements, you can generate various kinds of smeared Wigner distribution. Now, it's not necessary that the Arthur-Kelly measurement has to be done only for position and measurement. It can be done for spin variables also, and there is some very interesting work in the literature. Now I turn to a different question. I will not try to cover my entire talk, and after some reasonable point, I will stop so that we can have some discussion. Now we ask a very intriguing question. Can one devise a measurement scheme, even for a restricted class of circumstances, such that full information can be obtained about the single unknown state, not ensemble, single, without affecting the state? Now, if you could do that, then you can accord to it an element of reality, because the state is unchanged, and you can make the same measurement, and it looks closer and closer to what a classical measurement is. This is clearly against the law of quantum mechanics, and without any deep thought, I already did that. We can say it is impossible in general. But can we do it for a restricted class of states? So Aharonov, Anandan, and Weidman made a proposal. They said we can't do it for all wave functions. So not every wave function can be given an element of reality. But for some class of wave functions, we can give a reality, even though one can ask, what's the use of that? Because of superposition and evolution, etc. If you give reality to some small sector of the states, it really is no big deal. But anyway, they said, you take Hamiltonians, which are non-degenerate spectrum. Okay? But we don't know which Hamiltonian it is. So in addition to the Hamiltonian, you let this unknown Hamiltonian be present at all times. And this is called the protecting Hamiltonian. And we also do not know which non-degenerate eigenstates the system is in. It's in one of the non-degenerate states, and that's unknown. So this experiment, this proposal covers a small set of states which are unknown. But remember, we are performing on a single copy, not on an ensemble. So here's a little bit of a theory. Formula are not, good thing in talks like this, but I'll just point out some generalities. So you take a two-level quantum system, so which is non-degenerate eigenstate. Now the interaction time t is now taken to be very, very large, and the total Hamiltonian has an probe part, system part, and an interaction part, and the various restriction you pose so that you can get something. And if AI are the eigenstates of probe observable QA, since QA commutes with HA, it can also be simultaneously an eigenstate of HA, etc., etc., etc. Now, if you just go back and look at this, the only thing you have to notice is that apart from HA, what is there is system Hamiltonian plus the perturbation. So now if I restrict to an eigenstate, AI, then QA can be replaced by AI, and we can ask, what are the eigenstates of this object? And the total eigenvalue of the Hamiltonian consists of the probe part and this. The important point, since this is the perturbation, the correction is entirely given by first order perturbation theory, where you simply take the expectation value of the perturbation, and this will be the solution to it. Now, it turns out if you put everything together, the correction is going as 1 over t, and you're going to look at, for very, very large time evolutions, So the phase grows as T, and that T compensates for this 1 over T. And what you get, you can follow this in paper, that after a long time, the system is in the same state as it started. And the probe state has its own evolution, which you can neglect if the probe Hamiltonian is small. But lo and behold, the probe state, apart from this free evolution, is shifted by an amount that is the expectation value of the observable QS in the unknown state. So the system hasn't changed, and by looking at the apparatus, you can read off what is the expectation value of an observable in this state. And now if you do it with sufficiently many observables, you can determine the state. So the miracle has been achieved. And the key is that the apparatus and the system remain disentangled, unlike the von Neumann type measurements. And we will call this ideal because we're going to take the limit t going to infinity. So to get an appreciation of what's happening, suppose you did a Stern-Gerlach experiment, where in addition to the inhomogeneous magnetic field, you put this protective Hamiltonian. Now, instead of the silver atoms going into two places, they go to only one spot, and the location of that spot gives you the expectation value of the observable. So as is typical of Aharonov, is of course a very great thinker, but also makes very provocative statements. And they said this gives reality to the wave function, and many gullible philosophers have taken it seriously and they have written several books on it. But it turns out no reality can be given, even in this setup. The point is, in practice, T can be very, very large, but never infinite. So there's always an entanglement, which is very small, but it's there. And if you're making an experiment on a single copy, because of this entanglement, even though the probability of finding the wrong state is very small, you can't rule it out. So if the measurement gives the wrong state, then the state is not protected, and there is no reality that can be given. So if you want details, please read our paper. Now, Souvik, can I take another 10 minutes or shall I stop here?
Sir, you can take 10 more minutes, no problem.
Okay. So now I come to a type of measurements called weak measurements, also proposed by Aharonov. Now the measurement interaction is of the same type, impulsive, as in the von Neumann. But the initial probe state is not a sharp Gaussian, but it's taken to be very different. This is one version of the weak measurements. Now the pointer states of the von Neumann measurements of the momentum states, and being a continuous variable, a practical realization for the probe is by narrow Gaussian packets. That's the von Neumann measurement. The width of the wave packet in momentum space is delta p, is very small then, and the width in position space correspondingly has to be very large. Now the main difference now is that the initial probe is taken to be very broad in momentum distribution and therefore very narrow in position space. Now, when you take such a probe state, it will fail to satisfy the requirement that distinct outcomes will correspond to distinct post-measurement state. And again, I have to skip a lot of the mathematical derivations. So this is the probe state. In the von Neumann case, delta p is very small, delta q is very large. In weak measurements, delta p is very large and delta q is very small. And you can go through, since it's impulsive, the measurement interaction is very simple, and you can very simple to go through the mathematics. The end result is that you can represent the post-measurement state in the following sense, where this is a definite or a sharp momentum state, and this is an eigenstate of the system, and this is some probability amplitude. So if the outcome of the probe is P, then the system, quote unquote, collapses to psi P. But if I take two different values of P, the two different psi P's are not orthogonal. This is quite opposite of what happens in the Feynman measurement, where if the outcomes are two different eigenvalues, the states are the eigenstates which are orthogonal. Okay, then you can work through the mathematics of this weak measurements. And this in particular example of what is called the positive operator valued measurement is a jargon, but the spirit of those is captured by this. Now, the probability of the outcome is this NP square, and for very small values of the outcome, the system state is very, very close to the original state, so it's not affected at all. So that's why we call this a weak measurement, because it doesn't disrupt the system dramatically. Okay? But what's the price you pay for that is the information is also very, very little. For large and positive P, on the other hand, the state of the system does change a lot. And there is a lot of information, but the probability of getting those is exponentially small in this. Therefore, it is exponentially large occurrences or reasonable occurrences which give not no information, but very little information. Together, they constitute to give the complete information about the state. Okay? So that is the beauty of the weak measurements, and it obviously has to be done on an ensemble. The one weakness of this is the variance is very large, and therefore weak measurements of this type will require huge ensembles for comparable accuracy. You can again ask, what is the post-measurement state? It's of course a mixed state, but the amount of mixture is very small because delta P is very large. So the weak measurements, they maintain the purity of the ensemble to a very high degree. Whereas in strong measurements, purity is dramatically lost. And this we have proposed is to, as a pragmatic application of these weak measurements. Now there is the weak value measurement. Very quickly I'll go through it. Now in weak measurements, we consider all possible outcomes, but if you post-select the outcomes, then you can define what is called a weak value. So you have chosen an observable S, made a measurement on an unknown state psi, but post-select the outcome states to be B. Now, without going into the details of what this weak value is, note that it is invariant if you make a phase measure change on the wave function. So it lives on the state space, which is the space of rays, and therefore is an observable. And it's not correct what our quantum mechanics books say, that only probabilities are observable in quantum mechanics. Weak values are also observable in quantum mechanics, and they're not probabilities because they're not even real. They're not bounded. And these are what are called Dirac-Kirkwood quasi-probabilities. There are also special cases of Bergman invariant. It need not even be real. Therefore, one model of weak values is that the observable content of quantum mechanics is not just probabilities. Okay? So if these weak values can be directly measured, and you have to do a post-selection, and it's obvious that the weak value can be larger than the largest eigenvalue, it can even be complex. So a lot of confusing and misleading statements appeared initially about these weak values. For example, the title of one of their papers says, the result of a measurement of a component of spin of a spin-half particle can turn out to be 100. Okay, but it hides the fact that it's a weak value measurement, not an eigenvalue measurement. This is misleading, as the measurement is not of the standard type. It's best to view these as yet another variety of quantum measurements yielding the so-called weak value as the outcome. Now, you can determine states through the weak values, and that's called weak value tomography. So if you take a density matrix, you have to determine the expectation values of, say, a spin case, Sx, Sy, Sz, and it turns out that you can use the weak value of just the Z component of the spin. Normally, you would have to measure all three components, but we now can measure only the Z component, only one component. You determine the weak value, and then it turns out that the state is completely determined in terms of this one single complex weak value. And so you can, this is weak value tomography. Now you can ask, in the state space, you can talk about a metric, and it's easy to evaluate this. And it turns out the metric is conformal. So there are a lot of beautiful properties of the state space parameterized in terms of these weak values. For arbitrary spin states, we have proved similar results, and the metric is no longer conformal, but in all cases, the metric is that of a Kähler geometry, and the geometrical content comes out explicitly in terms of these weak value coordinates. So I end with giving some useful references. Now for projective measurements, there are the, I leave the slides with the organizers. Feel free to look at it and send me any comments that you want. And these two references also have reference to our original work with Tavish Qureshi. And then I have an archive paper on 3 results on weak measurements. And these results on weak value measurements for both pure and mixed states were obtained in collaboration with Rajat Krishna and Sai Smriti. And our latest paper is on POVM generated quantum trajectories. It is on the archive. And I recommend this because we give a very thorough discussion of the entire measurement issue based on von Neumann's original papers. Thank you for your patience.
Thank you, sir. It is very enjoyable and enriching talk, and I have already got so many requests from different participants to share, so that I can share your PPT or the video that is
Yes.
being recorded.
Feel
With your
free.
permission. Yeah, yes.
Yeah, no permission needed.
Okay,
The
sir.
spirit of CASI Lab should be free dissemination of knowledge. So
Okay,
go
sir.
ahead.
Thank you, sir. And sir, to you, we have conveyed your remembrance to Professor Crowley, but he could not join because of health issues.
You know, he's 96,
Yes.
and
yes.
therefore, you know, we have to understand that.
Yeah. Now, sir, if I move on to question answer session. I have already forwarded you in WhatsApp 3 questions.
Yeah.
With name of the question set and the person who is asking the question. And anybody who is willing to send questions, please feel free to WhatsApp me so that I can send it to sir.
I'm opening WhatsApp
Yeah,
and taking a look at that. Give me a second.
sure, sir.
Question 1 from Saugata Bhattacharya of IIT Indore. Hello, Saugata. In Arthur Kelly measurement discussion, as incompatible observables always adds noise, does this added noise can single-handedly affect entanglement in an entangled system? If yes, then what about single particle entanglement? Now, this is a genuine source of noise, and I expect it'll affect many things. In particular, I have not thought through your question, but it's an important question and worth pursuing. And if you want, we can exchange some notes. I hope that satisfies you. Second, from Professor Surjit Sen. Hello, Surjit. Thank you once again for this invitation and your bold venture. I once again wish all of you the very best. If the Hamiltonian is diagonalized in a particular basis, does that basis give correct picture on measurement? It is, if you are keeping decoherence in mind, it is the diagonalization not of the Hamiltonian, but of the density matrix. Okay. Now, the density matrix cannot be diagonal in more than one representation. So, which representation it is diagonal determines what the outcome of the experiment is. And they should all give the same result, but there is no more basis independence as in Schrodinger and Heisenberg evolution of quantum states. That's lost. Let me come to the third question. Souvik Rai. Hi, Souvik. Same message to you as to Surjit Sen. Since measurement plays a central role in defining observables in quantum theory, do you think the measurement postulate should be regarded as a fundamental action, or could it eventually emerge from a deeper theory of system environment interaction, such as decoherence? Now, this is the million-dollar question. Now, we have to go through the decoherence theory very, very carefully. Because in the decoherence theory, you're trying to look at the interaction of the probe and system with a very complex environment. And you cannot treat this complex environment accurately. So you will have to ignore some aspects of the environment. And this is usually done through so-called partial trace, etc. Now, if in doing partial trace, you have already assumed some sort of a collapse of the wave function, then decoherence conceptually has not solved anything. Okay? And therefore, we need to look at decoherence both from a theoretical point of view, many body theory and so on, as well as controlled decoherence experiments to answer this. This is really the million-dollar question about quantum measurement theory today.
Thank you, sir. If anybody else has any question, you can WhatsApp me. I'm giving you 5 minutes so that I can share the question to sir. Otherwise, I'll request Shurajit sir to put some closing remarks for today's session. Professor N.D. Haridass, who joined late, to them, I'm saying Professor N.D. Haridass is our inaugural speaker, who has given a wonderful and enriching talk, and we are very much blessed that we could contact him. Thank you, sir, so much.
Thank you very much. Thank you.
Sir, if you want to say something.
Just to mention,
Yeah.
thank you, Professor Haridass, for your excellent talk and kind enough to join in our venture. And actually, we have tried to convey your message, your audience to Professor Puri, and we mentioned he thank you, and but because of health issues, he could not make this attending talk. So thank you, sir.
Thank you. Thank you.
We need to be with us in future. And thank you.
Thank you, sir, and I thank all the participants for actually joining to this auspicious occasion. And thank you all. We'll be meeting soon. The next week with another talk by Professor Prashant Panigrahi of IISER, Kolkata. We hope that we'll be again have some fruitful discussion on some other topic. Thank you so much and good night. See you soon.
Good night. Good night.
Good night.